In today's lesson, we're looking at the differences between linear functions, quadratic functions, and exponential functions. Basically, we're looking at how would we know if I was given an equation, how would I know? If I was given a table, how would I know? Now, if I was given a graph, how would I know? Let's get started. First, we're going to look at linear functions. Remember, a big thing about linear functions, and it has the word line in it, meaning that for my graph, it would be a straight line. So when I'm given this graph of a straight line, I would know it's linear. The standard form of our function for linear functions is y equals mx plus b. We've seen that one for a while now. That is the standard form for a linear equation. So in this example here, my equation is y equals negative 4x minus 2. This is my slope, and this negative 2 is my y-intercept. Right away I know it's linear because I have a slope y-intercept and I have just x. This x term is just x. There's no x squared to it. There's no exponent. It's just plain x. Now for our table is probably the trickiest, but we can go over it. I always want to look at my y values. So from 14 to 10, I did negative 4. That's my rate of change. When I go from 10 to 6, that's negative 4 as well. 6 to the next y value of 2 is negative 4. And last but not least, 2 to the next value of negative 2 is also negative 4. I have a constant rate of change. That's how I know it's linear. It's linear if I have that constant rate of change of negative 4. Those are all the same numbers. That's my rate of change. This graph over here is actually this table. So you could always graph the table too to check out if you're not sure if it's linear or not. Now we'll look at our quadratic functions. Again, we want to know how will I know that it's quadratic based on the equation, the table, or the graph given to us. First of all, let's just review. The standard form of our function for quadratics is y equals a times x squared plus b times x plus c. In my example function here, I have negative x squared. A huge note, a huge kind of red flag goes off when I see that x squared term. When I see that x squared term, I'm very certain it's quadratic as long as I don't have any other exponents in my problem. I can also see this written as y equals negative x times x. No exponent there, but when I combine that together, remember you'll add those exponents. The x's are multiplied together, so I add the exponents to get x squared. And negative in this case. So you can see it written both ways, either as the condensed form over here or as the expanded form over here. Both will simplify to that negative x squared. In our table, again, tables are probably the trickiest. We look at our y values changing because the x values are going up by 1 each time. That's easy, that's not a change, but let's look at the y values going up or down, like in this case. From negative 4 to negative 9, I have to subtract 5. What about between the next y values? What about my negative 9 to negative 16? Well, I have to subtract 7. What about to get from negative 16 to negative 25? I have to subtract 9. And to get from negative 25 to negative 36, I subtract 11. Right away, it's unlike the last problem. So let me just flip back to that slide. Because the last problem, my numbers came out to be the same. Here they are not. So I look at the difference between the numbers I just came up with. So I can automatically rule out it's not linear, but I have to see, is it quadratic? How I can tell is if I have a same rate of change between these rate of changes. So I kind of have to look at the second difference, as the programs will call it that we're using today. I look at the second difference. Well, to get from negative 5 to negative 7, I subtract 2. To get from negative 7 to negative 9, I subtract 2. And to get from -9 to -11, I subtract 2. So this second difference, this was our first one, did not match. So I kept going. The second difference, the difference amongst my rate of changes, was -2 each time. That's how I know it's quadratic. When all these second numbers, so let me highlight them, when these second differences are the same. In our graph, super easy. If I was given this graph, we would know it's a parabola, a U shape. Remember, we can do smiley face down in this case because it was a -x. Or you could also have the smiley face up. Our parabola up or down would signify that it's a quadratic function. Now we're going to look at our exponential function. Again, in this lesson, we're looking at how do I know it's exponential based on the function itself, so the equation, based on the table, and based off the graph. Let's get started. Standard form of this function is y equals a times b to the exponent of x. So right away, this exponent of x, meaning that x is in an exponent form, gives it away that it is an exponential function. So right away in my example here, I have y equals -2 times 3 to the power of x. That exponent of x tells me it is exponential. It's not x squared. It's not saying, oh, that's a squared term there. No, it's just saying it's an x term there, so it's an exponential function. When I'm giving a table, again, tables are probably the most difficult because you have to look at the rate of change between the numbers. So let's take a look here. If I am looking at my chart in my table, remember the x values go up by 1 each time. The y values will change. So let's see. The rate of change between the first y and the second y in my table is subtracting 4. Now let's look at -6 to -18. Well, that's -12. -18 to -54 is -36. You can see right away it's not going to be linear. When we go back in our chart, so let me just go back for a second. Our linear had the same rate of change, subtracting or addition, in this case subtraction. But as you see in the exponential table, that does not happen. They are not the same numbers. So that's our first difference. Okay, let's, like we did for quadratics, go to the second change. Well, I'm subtracting -8. To get from -4 to -12, I have to subtract 8. Well, what about -12 to -36? Well, I have to subtract, in this case, 14. Okay, that's not coming out to be the same numbers like it did in my quadratic. So right away I know it's not linear because the first numbers are not the same, so let's erase that. I know it's not quadratic because those changes in the second difference were not the same. So I'm going to think about not addition or subtraction, but multiplication. I'm going to think about multiplication here. Okay, let's go for it. -2, what can I multiply to get -6? Well, that's easy, -3. Well, actually, it should be a +3 because, yes, it's going down, but you're multiplying by 3 to keep that negative there. From -6 to -18, I'm multiplying by 3 again. And then same thing. My rate of change is not subtraction or addition, it's multiplication. When it's multiplication, I know it's going to be an exponential. So before we were looking at quadratics and linear with subtraction or addition, here I'll see multiplication. I have times 3 each time. That's how I know it's exponential function. My y values are increasing by a multiplied number. So it could be times 2, times 3, times 4. But the y values are increasing by a multiplied number. In our graph, we'll know if given this graph, it is not exponential. Also, these are all connected to these equation tables and graphs through this whole lesson. All reflect each other. So they're all looking at the same function here, just to let you know. But if I was given this graph solo, I would know it's not linear because it's not a straight line. It's not quadratic, it's not a U-shape. Big differences about exponential is that you have an asymptote. There's a line up here that it will not get to. It will not get to x equals 0. Looks like it's getting close up here, but it will never touch that x equals 0. And as you see too, we talk about steepness sometimes. My slope up here is definitely more shallow than down here. It's multiplying, which is why we looked at the table, but it's decreasing down here. It's going down way faster here than up here. So I don't have a constant rate of change or a kind of reflected U-shaped parabola. That would be like this for a quadratic, but I do not have that here. I have one side that is shallow like up here, so I'll highlight that in pink, the shallow part here, and then I have a more increased part down here. So a more shallow slope and a more steep slope down here.